All right, in this video, we're going to be working some AP Calculus area volume free response questions. And this first one, this one's no calculator. R is bounded by f of x and g of x. I think, let's see, f's going to be the one on top, that cosine, because it's going to start at 3. Or, wait, no. Nope, that's wrong, because when x is 0, it'd be negative 2 plus 3, which is positive 1. Okay, so f down here, g over there. G, when x is 0, would be 6 minus 2 is 4. Okay, that makes more sense. Okay, finding the area of R, we're going to integrate from x equals 0 to x equals 2 on g minus f. 0 to 2, top minus bottom would be g of x minus f of x. So 6 minus 2 times x minus 1 squared minus negative 2 minus 3 cosine of pi over 2x. Okay, that's kind of involved. So I'm going to anti-differentiate. I think I can just add 1 to the power and divide by new power on this, but I'm going to think about it after by taking the derivative. If I took the derivative of this thing, I'd have 3 times that thing squared, and then the derivative of the inside's 1, so yeah, that looks good. 6x plus 2 more x, I'm going to just go ahead and combine that and make 8x. And then anti-differentiating negative 3 cosine of pi over 2x. So I would think negative 3 sine of pi over 2x, but I'm going to need to divide by pi over 2. So it's like multiplying by 2 over pi. So this antiderivative had it all. From 0 to 2, and that's going to be, okay, 8 times 2 is 16, minus 2/3 of 1 to the third, minus 6 over pi sine of pi, which is going to be 0. And then when I plug in 0, I'm not going to get all zeros. I'm going to get 8 times 0 minus 2/3 of negative 1 to the third. So that'll be positive 2/3. And then sine of 0 is 0. So to be subtracting another 2/3. So I'm going to end up with 16 minus 4/3. And I think that'll be 44/3 or something. But that's far enough. All right, R is the base of the solid. At each x, the cross-section perpendicular to the x-axis has area given by a of x equals 1 over x plus 3. Find the volume of the solid. Okay, so if they tell us the area of the cross-section, that's all we need to know to find the volume. We just integrate that area formula. And if it's something simple like 1 over x plus 3, we don't know what the shape is, but we know the area formula, so we're just going to take it on faith and integrate that. Cross-sections are taken perpendicular to the x-axis, so kind of the same representative piece as I was doing on A. That's going to move back and forth from x equals 0 to x equals 2. Okay, and I can anti-differentiate 1 over x plus 3. Okay, since x is greater than negative 3, I won't be needing the absolute value, but that's going to be natural log of 5 minus the natural log of 3, and you can make that the natural log of 5/3 if you want, but you don't have to. Right, but don't evaluate an integral expression that gives the volume of the solid when R is rotated around the horizontal line y equals 6. Okay, so 6 was the maximum possible value of h. Oh, whoops, that didn't even just read that far and realize that it was h and not g. Okay, but h equals 6 is right there. That would be like the axis of rotation. But then I'm going to need to get that stuff out of there because that's now kind of a little confusing. All right. R is rotated around y equals 6. All right, and so I know that this was h and this one was f. All right, and I'm going to need 2 radii. I'm going to need a large radius reaching from the axis to the far edge of the region that we're rotating. Okay, so large radius would equal top minus bottom, y equals 6 minus y equals f of x. Then I get a small radius reaching from the axis of rotation to the near edge of the region that I'm rotating. That's going to be 6 minus h of x. Okay, and then volume is going to be pi times the integral of a squared minus b squared as x goes from 0 to 2. And since I've clearly defined what a and b are up above, that's a suitable expression for us. We don't need to actually plug in 6 minus f of x in parentheses and square that in our setup integral. All right, part D, we're going to write but not evaluate an integral expression that gives the length of the graph of h between x equals 0 and x equals 2. So we're going to take h prime of x, and I guess I'm going to do that right here. H prime of x is going to equal 6, the derivative of that, 0, minus, take the derivative, outside prime, inside prime is 1, so it's negative 4 of x minus 1. So negative 4 of x minus 1, that's what's going to get squared, and it's 1 plus h prime of x squared that goes inside the square root. And we're going to integrate that from x equals 0 to x equals 2. Right. Now, number 2 allows the use of a calculator, and so I'm going to bring that in. All right, so I typed in everything just like I saw it, and I see what we're getting at here, this region here, region E. If we want to find the area of E, we've kind of got two options, and I think I'm going to show you both of them. Option 1 would just be integrating red from 1 to 3.69344, and then blue from 3.69344 to, looks like 5. Okay? And that is one option. The other option would be right minus left, because that'll be pretty easy. Consistently right minus left as y goes from 0 up to 1.30656. Okay, but I'll show you both and show you the same thing. So if I was going to do it with respect to x, I would need to say log x equals 5 minus x at x equals, solve that equation, 3.69344. Right, and then I'm going to say that area is going to equal, okay, first I'm going to integrate on red. And that started at x equals 1 and ends at 3.69344. And red was y equals log x. And we're using a calculator anyway, so the fact that we don't know an antiderivative for that is not a problem. And then we would be adding that to, if I integrated on blue, that would be the integral from 3.69344 up to 5 of 5 minus x. Now I'm going to integrate from 0 to 3.69344 on log x dx plus integral from 3.69344 up to 5 of 5 minus x dx. And I'm going to get that 1.9858 number. Okay, but I also want to show you that, okay, I could think about it in terms of right and left. This would be if y equals 5 minus x, x is going to equal 5 minus y. And let's make sure you can see that. Then if y equals log x, x equals e to the y. So, or like alternatively, I could integrate right minus left, 5 minus y minus e to the y. And that would be, well, let's say, just say I'm still solving that same equation. That would be 1.30656. So I'm going to integrate y equals 0 to y equals 1.30656 on that, and we'll see that we get the same number. Uh-oh, what has happened here? I see what happens. I didn't type that in right here. That should have been a 1. And then I'm going to get that 2.985804105 number. There we go. That's more like it. Okay. I guess it's a good thing I did it both ways. Definitely easier to do it with respect to y, if you've got a calculator and you've got that experience. But if you want to split it up into two areas and do it with respect to x, because that looks more logical to you, then it's totally what you should do. So 2.986. All right, find the volume of the solid generated by rotating E around the y-axis. Okay, so I will need, I'm going to draw my own diagram for this one. That's the y-axis, and this is kind of like, that's pretty good drawing. Okay, so the large radius would start at the axis of rotation and reach all the way across the region that we're rotating. I'm going to just kind of copy in the x-coordinates that I found earlier, 5 minus y, and the y-axis is the set of all points where x equals 0. Then I'll need a short radius running from x equals 0 to x equals e to the y. And so I'm going to say, I might just set this integral up once, though, because I'm going to use a calculator for it. Since we're rotating E around the y-axis, around the vertical axis, we'll need those horizontal lines to range from y equals 0 at the bottom up to y equals 1.30656 at the top. And then large radius squared is going to be 5 minus y minus 0. Small radius would be e to the y minus 0. Alright, and so I can get rid of these. I shouldn't have gotten rid of that one, but I'll need a pi in the front. From y equals 0 to y equals 1.30656 on 5 minus y squared minus e to the y squared. Well, dy, and then I'll get 58.280. Right. There is a value of k for which the horizontal line y equals k divides region E into two regions of equal area. Write an equation involving an integral whose solution gives the value of k. Right, so I'm thinking I just want to draw kind of the same sketch, curved, and then a straight line there. All right. So kind of like that, where it's cutting it and the area above the line y equals k is equal to the area below the line y equals k. And so if we think about the area with right and left, or with respect to y, like we did kind of in the second integral in part A, then this won't be too bad. We'll just think about, okay, really this region down here where I'm looking at adding up right minus left as y goes from 0 to k, that needs to be the same as the integral going right minus left from k up to the 1.60356 number. Okay, so the idea is we're going to integrate from y equals 0 up to y equals k, and then that's going to be equal to the integral from k to 1.30656. And then right minus left is still going to be the same thing it was up here, 5 minus y minus e to the y, because we're talking about area. Okay, that's us writing an equation involving an integral. Now, if we did, now with Desmos, if we needed to solve this, we actually could without too much difficulty. I'm going to say, I'm going to graph both of them in terms of k. So from 0 up to k of 5 minus y minus e to the y. And there might be a better way to solve this equation on Desmos. That's something I definitely think I could do. Actually, I don't exactly want a slider, right? Because I don't want to, just have it be different numbers and try to find out where they are each other. I think I'm going to just call this a function of k. Yeah, there we go. And so for now, I'm going to turn these things off. And then the other integral that I want this to be equal to, I'm going to call this a different function of k, equals the integral from k up to 1.30656 on the same thing, 5 minus y minus e to the y. And then they should intersect somewhere between 0 and 1.30656, right? And they are, and that's, okay, 1.30656. Okay, yeah, that would make sense. And yeah, that's too far. That's at y equals 2, which is, up above. But right here would be where that happens. K would be equal to 0.421 if we needed to find that value, which I don't think we really do in AP Calculus, but you never know. Especially with Desmos these days, there's kind of like more we can do. So number 3 is also a calculated question. Get rid of these. Let's say we're going to graph f of x equals x to the 4 minus 2.3x cubed plus 4. Okay, and then this one is going to be the line y equals 4. Turn that on. Okay, so that looks just like we're seeing in the figure. Okay, we've got all of this, and find the volume of the solid generated when r is rotated around the horizontal line y equals -2. Okay, so that would be, down here somewhere. I actually draw my own sketch of this one, I think. So it goes. Oh, let's see. Just have to be more confident because that won't snap too. But that looks fine to me. And we're going to rotate around y equals -2. So we're going to need large radius and the small radius. Okay, so for the large radius, I reach from the axis of rotation to the far edge of the region I'm rotating. And that would be y equals 4 minus y equals -2. A is going to equal 6. Okay, then B is going to be top and bottom from the axis of rotation to the near edge of the region that I'm rotating. So that would be top is f of x minus bottom was -2. So f of x plus 2. And then I'm going to say volume is going to equal the integral from x equals 0 to x equals the intersection point, which I'm going to have to find out here in a second. But it doesn't say anything about that place. And okay, we've got x equals k, so I won't use that letter. I'm looking kind of ahead to see what other letters are in this problem. I already used capital B. Maybe I'll call it P or something. Okay, so I'm just going to say, what is a, oh, it's, so f of x equals 4. I'm going to need that x coordinate of intersection. That's at x equals 2.3. Okay, that does make sense. Okay, so I don't even need to give it a name. We're going to call that 2.3. Okay, so 0 to 2.3 on a squared minus b squared dx. Because those radii would slide back and forth along the x-axis. And then we can let the calculator do the rest of it here. So I'm going to type in a equals 6 and b equals f of x plus 2. Okay, we don't need that. Then I'm going to say pi times the integral from 0 to 2.3 of a squared minus b squared dx, and I'll get 98.868. Next, region R is the base of a solid. For this solid, cross sections perpendicular to the x-axis are isosceles right triangles with a leg in region R. Okay, so I'm going to be looking at it like, okay, so this is the base of the isosceles right triangle. The height will be equal to the base. Base equals top minus bottom was, okay, I guess we didn't need that yet, but that's going to be 4 minus f of x. Okay, area is going to equal 1/2 base squared, which would be 1/2 of 4 minus f of x squared. Okay, we want to integrate that area formula to get the volume. So I'm going to say that volume equals the integral from x equals 0 to x equals 2.3, still the same. The area formula was 1/2 of base squared, so 4 minus f of x taken to the second power, and we can type that into the calculator. Won't need the pi. Can put a 1/2 on the outside. Definitely won't need that. What is it? 4 minus f of x squared. All right, and that's going to be 3.574. The vertical line x equals k divides r into two regions with equal areas. Write an expression in an equation involving an integral expression whose solution gives the value of k. Right, so it's like the other one we did on the first example. I think it might be, maybe around there. X equals k, but the idea is that the area on the left will be equal to the area on the right. Top and bottom is going to stay consistent, so it's going to be easy enough for us to compute an integral. All right, we know that the situation starts on the left at x equals 0, and so we're going to integrate from x equals 0 up to x equals k on top minus bottom. That would be 4 minus f of x. And that would be equal to the integral from k up to 2.3 of the same thing, because top and bottom didn't change. And then as far as finding the perimeter of R, and again, this is the type of thing that we could pretty easily solve this if we graphed y equals the integral from 0 to k of 4 minus f of x dx, and then also graphed y equals the integral from k to 2.3 of 4 minus f of x dx. We turned off the other graphs, so we don't really want to look at. There would be only one that was happening between 0 and 2.3, and that would be 1.578, and that must be the value of k. All right, just showing you that, just in case you ever did need to find that value in the future. Right, and so finding the perimeter of R, that'll be, I need to find, okay, the blue length is going to go for 2.3 minus 0. Okay, so I'll kind of paste that in. All right, the blue length here, that was x equals 2.3, that was 0, that's a width of 2.3. So it'll be 2.3 plus, and then I'm going to need to run an integral to get the length of that curve. But since I'm using a calculator, I should let the calculator do the work for me. We called this function f of x, so I'm going to be integrating from x equals 0 to x equals 2.3 on the square root of 1 plus f prime of x squared dx. And we can just let the calculator do that work for us. So I'm going to have 2.3 plus the integral from 0 up to 2.3 of the square root of 1 plus f prime of x squared dx. And that would be 8.967. Now, we're back to a no calculator scenario, so get rid of that. Let R be the region in the first quadrant bounded by the graph of y equals 2 root x, y equals 6, and the y-axis. All right, find the area of R. Okay, now we could do right and left, but I'm seeing top and bottom as an option, and that won't require me to really solve for anything. So I'm just going to kind of, best I can, draw a sketch of this. Right there we go. That's going to be, if I integrated top and bottom, I'd be integrating top was 6 and bottom was 2 root x. So 6 minus 2 root x is what I'm going to integrate from x equals 0 to x equals 9. And that's going to be 6x minus, add 1 to the power, would be 3/2 power, divide by 3/2, it's like multiplying by 2/3. I'm just going to think about that antiderivative real quick. If I took 3 halves, I'd be doing 12 over 6 is 2. Yeah, okay, that makes sense. Divided or evaluated over 0 to 9, that's going to be 6 times 9 is 54 minus 4/3 of 9 to the 3 halves. Okay, 4/3 of 27, that feels like 36. Minus, when I plug in 0, I'll get 0 and 0. Okay, so 54 minus, yeah, 9 times 4 is 36. That'd be 18. Okay. And then writing but not evaluating an integral expression that gives the volume of the solid generated when R is rotated around y equals 7, which is just slightly above that. Okay. So I'm going to draw the axis of rotation. It's right above. And I'll need 2 radii. Okay, large radius will start at the axis of rotation and reach all the way across the region. So A will equal top is 7 minus bottom is 2 root x. Then B would be top and bottom from the axis to the near side. Would be 7 minus 6, okay, which is 1. And so I'd be integrating pi times 7 minus 2 root x squared. And you could just write a squared if you'd already clearly defined it out to the side. But just to really emphasize what's going on here, to do this, this is going to get integrated with respect to x as x goes from 0 to 9. Okay. Then, region R is the base of solid. Each y, where y is between 0 and 6, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base. All right. Probably should have started with the horizontal line. That one tended to look a little better. About like that. And so we're going to be thinking about cross-sections taken perpendicular to the y-axis. Be right here. I'm going to need a right and a left, so that would be x coordinates. I do believe that was the y-axis, so that's x equals 0 on the left. But if y equals 2 square root x, then half of y equals root x, and x is going to equal, if I square both sides, I'd get 1/4 of y squared. Okay, so the base of the rectangle is right minus left. Base equals 1/4 y squared minus 0. Height is equal to 3 times the base, which is going to be 3/4 of y squared. Area equaling base times height, because it's a rectangle, is going to be 1/4 y squared multiplied by 3/4 y squared, which is feeling like 3 over 16 y to the 4. And so that's what I'm going to integrate as y goes from 0 to 6. Okay, but then it said write, but don't evaluate. Okay, that's... Yeah, I guess you would need to know 6 to the 5th power, and I don't know what that is. And the 6 and 16 don't have that good of common factors, so... Okay, that's going to be far enough. That's our setup. Maybe I'll just move this down here. Emphasize that that's our answer. All right. Had I known that it was a setup and not evaluate, I might have just said 3 times 1/4 y squared squared, which would have, of course, been the same thing. But okay, this one is calculator square root x and x over 3. Find the area of G. Okay, so I think we're going to need that for an intersection immediately. So x over 3. I'm just going to type it in first and then bring in the calculator. So square root x. Oh, no, I think I could have figured out where those intersected pretty easily. That's all right. So I'm going to show the calculator. And finding the area of G, okay, we're going to do top minus bottom, red minus blue from 0 to 9. So, and integral from 0 to 9 of red was the curve. That's going to be square root x minus x over 3. Doesn't really seem like a calculator question. Maybe, yeah, we're probably going to be, we're going to be computing a washer later. Yes, that's definitely a calculator. So square root x minus x over 3 dx, and that would be 4.5. Right, find the volume of the solid generated when g is rotated around the vertical line x equals -1. Okay, so I'm going to, best I can, draw a sketch of region G. X equals -1 would be over here. This one would need 2 radii. The large one would reach all the way across the region. The small one's going to reach just to the near side. Okay. And I'm going to need x coordinates for all these. If y equals x over 3, x is going to equal 3 times y. And if y equals square root x, x is going to equal y squared. Okay, on the left, we have x equaling -1 both times. So right over here, let a equal 3y minus -1, and let b equal y squared minus -1. In order to find the volume, we'd be integrating pi a squared minus pi b squared. That's how we're going to want to type it into the calculator. This will be with respect to y, because a and b both depend on y, and y goes from 0 up to 3. Okay, but now at this point we've got some work to do. We have to type in a equals 3y plus 1, b equals y squared plus 1. We definitely don't need to be looking at those. Those aren't really helping us. Pi times the integral from y equals 0 up to y equals 3. Let's raise that up a little bit. Of a squared minus b squared dy, and that's 130.062. The region G is the base of a solid. For the solid cross sections taken perpendicular to the y-axis are squares. Find the volume of the solid. Okay, so this is actually going to be a really good contrast with part B. So I'm going to try to draw the exact same diagram. Okay, and then draw one of these cross sections taken perpendicular to the y-axis. Okay, so whereas we had 3y and y squared interacting with that x equals -1 each individually, this time, since the cross section is in the region G, we're going to be interested in 3y minus y squared. So over here I have x equals 3y, over here x equals y squared. So the base of my square is equal to 3y minus y squared, and the area of a square is equal to base squared, so it's 3y minus y squared, and then our volume will be the integral of that as y goes from 0 to 3. Okay, and it actually asked me to find the volume of the solid, so I'm going to need to do that. Okay, I definitely don't need the pi. I just need 3y minus y squared, and I need to square that, and so that would be 8.1. And if we wanted to find the perimeter of G, then I'd be thinking about it's kind of two pieces. Let's see, so I could probably do some Pythagorean theorem on this. From 0, 0 to 9, 3. Yeah, I'm just going to do that old-fashioned way. 9 squared plus 3 squared, square rooted. That'd be the length of the line segment, plus the integral from x equals 0 to x equals 3 on the slope of red. So, or not exactly the slope, but the formula that involves the slope. So it's the square root of 1 plus the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And if I was going to use this for more than one thing, maybe I'd simplify it, but I'm just going to let the calculator do the work. And say the square root of 90 plus the integral from 0 to 3 of the square root of 1 plus dy dx squared, so 1/2 x to the negative 1/2 squared dx, and I'll get 13.098. I've got a new calculator question, so I'll type in those functions. Y equals sine of pi x, that's definitely the one on top, and I've found that if you type them in as f of x and g of x, that actually is kind of helpful on the calculator side. Okay, and then I might write g of x equals x cubed minus 4x. Now I won't be writing that on my paper unless I have clearly defined it on the paper f and g, but I'll just refer to them as their things because those aren't particularly complicated formulas. I am going to restrict the viewing window to 0 to 2 because that's kind of a lot of graph. All right, there we go. And that's going to be a lot more like what we're seeing in our diagram. All right, so finding the area of R is going to be the integral of red minus blue, top minus bottom, as x goes from 0 to 2. So let's say integral from 0 to 2 of red was sine of pi x minus blue is x cubed minus 4x. I'm just going to be really careful about parentheses here. If we don't have names for them, then I'm going to be, but on the calculator, definitely don't even take the chance with parentheses, just integrate f minus g, red minus blue, top minus bottom. That's going to be 4 units of area. This is great. The horizontal line, y equals 2, splits the region R into 2 parts. Probably not equal, though. Definitely not equal. Right, but don't evaluate an expression involving an integral for the area of the part of R that's below this horizontal line. Okay, so we're going to need to find these special points right here. And so I'm going to be interested in where x cubed minus 4x equals negative 2. And that's going to equal... or that's going to be at x equals, let's see, 0.53919 and 1.67513. So I'm just going to copy those in. 0.53919, 1.67513. Okay, and now since I'm not going to really need this special part of R again, I'm not going to give these x values special names. I'm just going to use those as my bounds of integration. And it says right, but don't evaluate, so this is my answer, 0.53919 up to 1.67513. Top minus bottom in this case would be 2 minus the cubic polynomial. So 2 minus x cubed minus 4x dx. Oops. Like that. Okay, and then R is the base of a solid. For this solid, cross sections perpendicular to the x-axis are squares. Let's get rid of this drawing because it's not going to be in my way. And I think I'm going to draw my own sketch of this region. All right, and I'm going to draw one of these cross sections that's perpendicular to the x-axis. Okay, and that would be the base of the square. So the base is going to be top minus bottom, which is still this sine of pi x minus x cubed minus 4x. Area is going to equal 1/2 base squared. If I've already defined b, and I haven't done a washer problem also where I've, already defined capital B. I'm going to actually use that, and I'm just going to integrate 1/2 b squared dx, because that's a lot to copy again, and x is going to go from 0 to 2. So that would be my recommendation. Just define B is, it's going to be f of x minus g of x. You don't need to look at the graph of that. We're going to integrate from x equals 0 to x equals 2, 1/2 base squared, because that's the area of an isosceles right triangle. I don't know why I was doing that. It's not an isosceles right triangle, it's a square. Okay, so that would be 1 base squared. Okay, but that's more like it. And then I need a dx, and that'll give me 9.978. All right, now this one, the depth of the pond, I've always struggled to explain this one. Let me think about this for a second before I get too deep into it. All right, so I've kind of added in a little thing on the graphing calculator for us to, be viewing the little cross section from part C. And what I'm going to say about part D is that we're saying at each distance x from the y-axis, so that's like as I'm advancing k, right, this vertical bar goes side to side, and I've kind of tried to, draw that or describe this at various points, but I haven't actually put it in Desmos yet, which is kind of regrettable. But we see we're going back and forth, and it's this vertical line that always stays between blue and red. And what I wanted to say about it is that, okay, so at this depth right here, whatever, we're 0.6 units away from the y-axis, the depth is 3 minus 0.6, so that'd be 2.4. Okay, and it's always that same depth along this whole vertical line, which means if I kind of like went to the side of the small pond and looked at it, against that cross section would be a rectangle. All that to say, cross sections are rectangles. This is a rectangle cross section problem where the height is 3 minus x and the base is top minus bottom. So I'm going to be integrating, 3 minus x is the height multiplied by the base is top minus bottom, that same sine of pi x minus x cubed minus 4x. So in retrospect, I really wish I had written out let f of x equal sine of pi x and g of x equals x cubed minus 4x, because I could have just been like freely using that throughout the whole problem. But it's okay, I've gone this far. Okay, so that's what I'm multiplying. I'm going to integrate that with respect to x, and we're still going to let x go from 0 to 2. Okay, so that will be, but I've already got top minus bottom listed as b. Okay, and I feel like there's probably some way I could have used this to whatever. So I'm going to be integrating from 0 to 2 on, raise it up so you can see it, 3 minus x multiplied by b dx, and then that's going to be 8.3699, 8.370. Okay, I've got, let's see how many more of these I've got. Oh boy, I'm only halfway there. All right, so to be patient and get ready to do a lot more area volume practice, but this is good. This is what we need. So y equals log x, and definitely don't need any sort of restriction here, I don't think. And g of x equals x minus 2. Okay, yeah. See what we need. We're going to have some intersection points. These are not numbers I'm recognizing, so I'm just going to store them there. I don't need to actually see their points on the graph, though. Okay, when finding the area of R, I'm going to need to, let's see, rotate R around the y-axis. We're going to rotate R around a horizontal line. So I'm going to say, all right, log x equals x minus 2 at x1 equals 0.15859, and x2 equals 3.14619. Okay, then I'm going to be, area of R, it's going to be top minus bottom between x1 and x2. And actually, since I can see that I'm going to be doing another integration with respect to x later on, I'm going to actually call these x1 and x2. Right. and then top minus bottom would be the curve minus the line, and I don't think, as long as we're careful with parentheses, I don't think we need to define these as f of x and g of x, because there's only 3 parts, and part C we're rotating around the vertical axis, so we'll need to solve stuff back for x anyway. I'm just going to say it like this. Okay, but since over here I know I'd called red f of x and blue g of x, I don't have to worry about the parentheses. Integral from x1 up to x2 of top minus bottom, red minus blue dx, and I get 1.949. Volume of the solid generated when r is rotated on the horizontal line y equals -3. Okay, so I'm going to say something like that. Y equals -3 is just below that, or a little bit below that. And so I need 2 radii, a large radius going all the way across the region and a small radius just going to the near edge of the region. So large radius A is going to be, the curve was log x minus y equals -3, and then B would equal x minus 2 minus -3, so it'd be x plus 1. Type those into the calculator. But because I'm going to be, definitely didn't want to do that. I still need x1 and x2, and I've already got that integral ready from x1 to x2, so I'm just going to over here type in a equals log of x plus 3, and b equals x plus 1. Okay, turn those graphs off. You don't need to be looking at them. We need pi times the integral of a squared minus b squared dx. But if I'm using the calculator to run an integral, I have to write down the integral I computed, so that's going to be pi times the integral of a squared minus b squared dx between x1 and x2. And then that's where I got 34.199. And then we're going to write, but not evaluate, an integral expression that could be used to find the volume of the solid formed when r is rotated around the y-axis. So I'm going to draw another one of these. Okay, yeah, I think I can forgive maybe that log curve being a little weird looking. But if we're going to go around the y-axis, which they're not actually touching, if we look over here, there's a little bit of distance between here and the y-axis, and even as we go, up this way, there's a lot of distance between the y-axis and the red curve. This is definitely a washer scenario. So I'm going to need a large radius over here and a small radius over here. And I'm going to be mindful of the fact that I've already committed A and B to mean 2 different things. So I'm not going to call these A and B. We got capital R already committed. I'm going to just call them like U and V or something. So I'll let the large radius equal U. U would equal right minus left. On the right, if y equals x minus 2, then x is going to be y plus 2. And then over here, the y-axis is the set of all points where x equals 0. So U would equal y plus 2 minus 0. And then V, right, would be e to the y if y is log x, and then x equals 0, so v equals e to the y. And then the expression that could be used to find the volume of the solid, okay, I'm going to need to find the y coordinates of those points, but I'll reserve some room over there to do that. Okay, we're rotating, so it's pi r squared. So pi u squared minus pi v squared, and this is right but don't evaluate, so I'm going to stop there. I'm going to need bounds of integration, so I'm going to say, okay, y plus 2 equals e to the y at y equals, it's kind of a shame, I should have held on to those points, negative 1.841, 84141. and y equaling up here 1.14619. And these are going to be the bounds I'll put right down here. Right, and then that will be my answer. I can't see the point anymore. There you go. All right, now the next one. Okay, we've got R, S, and T. Okay, I think the original problem just had R and S, but then I added on T for some more excitement. So f of x, looks like that's going to be the one on top, e to the 2x minus x squared. And if it's being weird with you about the exponent, you just use parentheses. Okay, that will work. And then the horizontal line y equals 2. Okay, there we go. That's R and S. And then y equals 1. Right there. Okay, so I've got R, S, and T. Now, are we going to find eventually... Oh, yeah. We're going to find the perimeter of T, and that's going to be a little bit tricky. That's something I added, and I think if we zoom in really closely, yeah, this is good on Desmos. It was really hard to tell on the TID4, and on the diagram, it makes it look like T has just 4 sides, but it actually has 5. So we'll need to be careful when we go to do that. But for now, I'm finding the area of R is just going to be top minus bottom. I'm going to say e to the 2x minus x squared is equal to 2 at x equals 44606 and 1.55394. So I'm going to integrate top minus bottom from 0.44606 to 1.55394. Top minus bottom would be e to the 2x minus x squared. Minus bottom was 2. Okay, or red minus blue when I'm over here on the calculator. Integral from red minus blue dx, and that's 0.514. Okay, finding the area of S, that's going to be a little bit trickier. We're going to have to divide that up into 3 parts. So I'm going to just kind of trace that. It's not exactly a trapezoid, but I actually like the look of this for the sake of, yeah, what I need to do here. So what I'm going to do is I'm going to split this up into kind of 3 integrals. First, I'm going to need to integrate, that was a curve. So that would be from 0 to 0.44606. And that's going to be top minus bottom would be the curve minus the... I'm thinking if there's a better strategy here. I think, finding the area of S when T wasn't there should be find the combined areas of S and T would be an equivalent question. Okay, no, but we're just going to need to cut this up into 3 pieces, and that's fine. Top minus bottom is going to be... But I'm going to be very clear over here. Let f of x equal e to the 2x minus x squared, just for my own sake right here. All right, top would be f, bottom would be 1. F of x minus 1 dx. Then I'm going to be having a rectangle in here, but I'm just going to do top minus bottom as an integrals. So from 0.44606 up to, what was I thinking? Okay, the next intersection, which was 1.55394 on 2 minus 1 is 1 dx. And then lastly, I would have this business here, and that's going to be the same top and bottom, f of x minus 1. I'm just going to integrate that from... Oh, yeah, I think what some people that were a little smarter in my class in the past have done is they've integrated f of x minus 1 from 0 to the second intersection, or to where it... let me show you on the graph, to this spot right here, to x equals 2. It had gone there, and then they just subtracted out the area of region R, which would have been smarter, but I'm already this far in, so I'm just going to say, all right, from 1.5539 up to, that looks like x equals 2. And we can see on the calculator, right, that's x equals 2, y equals 1 on f of x minus 1 dx. All right, and then that will be, let's call h f of x minus 1 just for ease, integral from 0 to 0.44606 of h dx plus, really I'm just going to put 1.55394 minus 0.44606 plus the integral from, let's raise that up, 1.55394 up to 2 of h dx, and then that's going to give me 1.546, which probably had to expend more effort doing that than you might have doing it a different way, but this works. Right, but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated around the horizontal line y equals 1. Okay, so I'm going to just draw r and y equals 1, draw the radiuses. So we'll let a equal top minus bottom. A is f of x minus 1. Yeah, and then b would be 2 minus 1. So my volume, it's right, but don't evaluate. So pi times the integral of a squared. And remember, I can only write f of x because I went and like very clearly defined let f of x equal this up at the very start. A squared minus b squared with respect to x as x goes from 0.44606 up to 1.55394. Okay, and then as far as the perimeter of T, I'm going to draw an exaggerated version of that. It's almost everything I'd hoped for. There we go. All right, so I've got this fifth side that I need to be a little bit need to be thinking about. I'm going to go over here and say, well, that's got a width of 2, this segment up here. So that's a 2. This is going to be a 1 up here. Then if it goes up to x equals 3, which I'm just going to assume it should say in the statement of the question, but when I added in that region T, I don't think I was thinking clearly. But we're just going to say this stops at 3 because otherwise it would have an infinite perimeter, right? We don't want that. So I'm going to say this is a width of 3. I'm going to need to get that height right here, which is going to be f of 3, right? Yeah, it would give me the distance from red to the x-axis. So I'm going to, I don't need any of these integrals now. Well, I guess I'll figure out the bounds of integration later. 2 and 3 and 5 and 1 is 6. Oh, but I needed f of 3. And so I get 0.04978, so 0.050. Okay. And so really all we have to figure out is, so I've got 3 and 2 is 5 and 1 is 6.04978. Plus, And I just have to figure out this curved piece right here. And if this is a calculator question, I'm just going to be integrating the square root of 1 plus, I've already defined f, so I can just say f prime of x squared. That's what I'm going to type into the calculator. And we're going to be integrating from x equals 2, that intersection point right here, up to x equals 3, because I've got to stop somewhere. So from 2 to 3 on that. And definitely I need to, rewrite the statement of this question. But 6.04978 plus the integral from 2 up to 3 of square root 1 plus f prime of x squared dx. And I'll get 7.486. After that, we've got f of x equals e to the x and g of x equals log x. All right, so e to the x and log x. Find the area of the region enclosed by the graphs of f and g between x equals a half and x equals 1. All right, so I think if you, let the calculator help you with this, it's a little easier to see. Okay, we're talking about between the two black bars, red minus blue. Okay, so we're going to say, I'm going to be integrating from x equals 1/2 to x equals 1. On red was e to the x was f of x, minus blue was log x was g of x. Okay, and we are going to integrate from 0.5 up to 1 on f of x minus g of x dx and get 1.223. Right, now we're going to find the volume of the solid formed when the region enclosed by the graphs of f and g between x equals a half and x equals 1 is rotated around the line y equals 4, which is up here. So okay, this is kind of a weird looking region. So again, oh, wait, so that's actually needs to probably extend lower. Curves up, and this one is like the opposite. Okay, and then we're going to rotate around the horizontal line y equals 4, about like that. Okay, so my large radius is going to be top minus bottom is 4 minus blue, that's 4 minus g of x. And the small radius from 4 to the near side would be 4 minus f of x. And all right, I'm good. So now I'm going to say find the volume of the solid. So pi times the integral of a squared minus b squared with respect to x. As x goes from a half to 1. Calculator, help me with that. Okay, now we're going to have to tell it what we mean by a and b. So a equals 4 minus g of x, and then b is going to equal 4 minus f of x. And then, okay, I don't need to be looking at that, 23.609. And after that, I'm going to be let h of x equal f minus g. So that's kind of like, if I just grabbed that stuff and got rid of got those, h is this vertical distance right here. Find the absolute minimum value of h of x on the closed interval 1/2 to 1. Okay, that's a closed interval. It's not an option. We need to justify our answer with a closed interval test. So we're going to go from 1/2 up to 1. And then we're going to say, where is h prime, which I know is f prime minus g prime equal to 0. And I bet there's only one point. It's going to be at that absolute maximum place. Or no, is it? I guess the curvature, I don't know. We've got a calculator, so it's easiest for us to investigate that way. Okay, I'm going to keep the 0.5 and 1 though. So h of x equals f of x minus g of x. Okay, yeah, we've got an absolute minimum, but what we are absolutely not going to do is go click on this point and be like, oh, hey, I graphed it. It was 0.56714. Or 2.33037 is actually going to be our answer. That's what we cannot do if we're hoping to get any credit in this class, right? Because our answers have to be justified with calculus. I'm going to graph y equals h prime of x. And I'm going to say, okay, h prime went from negative to positive at 0.56714 only. And you could go and write a couple of sentences and be like, okay, the only critical point of h on the interval 0.5 to 1 happens at 0.56714, and that critical point is the local maximum because h prime goes from, or is the local minimum because h prime goes from negative to positive. Therefore, since it's the only critical point on the interval and it's a minimum, it's the absolute minimum. But at that point, you would be much faster to just make your table. I promise. I sense that at least this year in my class, I've got students who are resistant to doing the candidates test, and it's like, oh man, if you look at what your other options are, you want to be doing the candidates test, and you do not want to just be yielding all the points at the beginning of the problem. That's not what a competitive student's going to do. So you just need to get your practice on candidates test and get to the point where you're feeling confident on it. When you see that closed interval, you know exactly what you're going to do, and you're going to get all the points you can, because it always works the same way. We test the endpoints, we set the derivative equal to 0, we list out the critical points, we run everything through, and so I'm going to make a table now. Call for table, x1 be 0.51 and 0.56714. And then rather than doing anything else right here, I'm just going to say h of x1. And I'm going to copy all these numbers down from the table. 2.342, 2.718. Sounds familiar. And then 2.330. Okay, find the absolute minimum. It's going to be right there. The thing they were asking for, I remember my advice recently has been, okay, always go back and triple check. What are they asking? I graded one in the summer recently where it was like I saw a lot of papers that had just like gotten lost in the candidates test, and they found the maximum instead of the minimum, or reported the value of x instead of the value of h of x. So I need the minimum value of h, and that's going to be 2.330. We're back to no calculator. So let f equal e to the x over 2, y equals 3, the graph of x and the y-axis. Okay, y equals e to the x over 2 is just going to be like y equals e to the x, but a little slower growing. Maybe about like that. So yeah, we know that y equals 3 will sit above it because that right there is at y equals 1. So let's say 3, point out that's 1. Find the area of the region. I'm just going to do top minus bottom. So 3 minus f of x dx as x goes from, okay, I'm going to have to figure out where e to the x divided by 2 equals 3. So I'll say x divided by 2 is the log of 3. And x is 2 log of 3, which you could call the log of 9, but I'm just going to say, okay, x goes from 0 to 2 natural log 3. Wait, no, not 1/2. That would be the derivative of e to the x over 2, so the antiderivative is going to be 2e to the x over 2. So we let x go from 0 to 2 natural log 3. Okay, this is perfect. So 3x would be 6 natural log 3 minus, when I plug in 2 log 3 over here, okay, the 2 log 3 goes into the exponent, gets divided by 2, so e to the log 3 is 3, so minus 6. When I plug in 0, I'd get 0 minus 2e to the 0 is 1. Okay, so I'm going to get 6 natural log of 3 minus 6 plus 2 is minus 4. Okay, find the volume of the solid generated by rotating r around the x-axis. Okay, this one would actually be pretty nice, I'm seeing. So I'm just going to draw my region. X-axis is going to be down here, so that's going to be a washer scenario. Large radius from the axis of rotation to the far side of the region I'm rotating, but A is just going to be, what's that, 3. And then the small radius would go from the axis to the near edge of the region I'm rotating. B would equal C f of x. Because I've got y equals 0 on the bottom, it's the x-axis. So, and if I square e to the x over 2, I'm just going to get e to the x. So this is going to be really nice. Pi times the integral from x equals 0 to x equals 2 natural log 3 of a squared minus b squared. That's going to equal pi times, 9x minus e to the x going from 0 to 2 natural log 3. Okay, now we might need to be a little bit more careful when evaluating because I want us to simplify this as far as possible. If this is a multiple choice question, like yes, you could plug in 2 log 3, so that would be 18 natural log 3 minus e to the 2 log 3. And I guess, in free response, you could stop there, but I need us to be able to evaluate this, so we're going to get the practice here. So 9 times 0 minus e to the 0. That, well, e to the 2 log 3 is equal to e to the log 3 times 2, like that, right? And so I could then also write it that way. That's going to be 3 squared. That's going to be 9. So I'm just going to need you to be aware of that. So 9 plus 1, that would be 8. So pi times 18 log 3 minus an 8. And that's a weird number, but that's the volume. So now lastly, find the volume of the solid generated by rotating r around the y-axis. Yeah, that'll involve a natural log. I think y'all know pretty well how to type stuff into the calculator, so I think I'm probably not going to go all the way. I'm just going to set it up. This video is already extremely long. All right, so this is going to be a disk scenario because we are only, rotating around the y-axis, which is part of the boundary of region R. So I'm going to say, all right, my radius reaches this way, away from the axis, and radius is going to be right minus left. If y equals e to the x over 2, x over 2 is going to equal natural log of y, and x is going to equal 2 log y. And over here, the y-axis, that's x equals 0, r is 2 natural log y. And so the volume of this solid is going to be pi times the integral of r squared with respect to y, and then y starts down here at 1 and ends up here at 3. I think I'd drawn that in an earlier diagram. And so we're going to let y go from 1 to 3, and that is a set up integral, and I think that'll be good enough. Yeah, you could run that through the calculator if you wanted. Let n be the region bounded by curves 4 over x and x minus 3 squared. Oh, and x minus 3. I was really confused. I was thinking about x squared minus 3. Okay, so y equals 4 over x. It does generally kind of look like this downward facing thing. And then y equals x minus 3 squared is going to be a parabola. So I think, well, close enough that I could just move it around. All right, that'll have to do. So that's my sketch. Find the area of region N. Okay, well, I can pretty clearly see it's going to be a top minus bottom from two intersection points. So I need to do some algebra and see where are these things equaling each other. Huh. No calculator, huh? Okay, well, I'm just supposed to see that x equals 4 is one of the intersections. I guess. Have I made an error in my algebra? No, I don't think so. Okay, well, maybe I'll just go in, and if I know 4 is a root, I can see that 4 over 4 and 4 minus 3 squared are the same thing. And maybe there's another obvious root here. I'm not seeing it, so I'm going to go and I'm going to do synthetic division. So 1, negative 6, 9, and negative 4. If I know that x equals 4 is a root of this polynomial, then I should be able to divide this cleanly. Okay, so I'm going to add. It would be negative 2, negative 8, 1, 4, 0. And yeah, like we said, it divides cleanly. And then I'm left with x squared minus 2x plus 1, which would be x minus 1 squared. Okay, and I knew I already had that x minus 4, so okay, I get it. So I'm going to have x equals 1 also. When I plug in 4 over 1 is negative 2 squared. Okay, maybe I was just supposed to be able to see that, but you know, sometimes I don't just have it like that. So that's x equals 1 and x equals 4. So finding the area, I'm integrating from 1 to 4 on f minus g. I'm going to anti-differentiate minus 1/3 of x minus 3 cubed, and that works because the derivative of x minus 3 is just 1. Okay, so that's going to be 4 natural log of 4 minus 1/3 of 1 cubed. Okay, 4 natural log of 1 is 0 minus 1/3 of negative 2 cubed. So minus 1/3 of negative 8 is plus 8/3. You know, you call it 4 log 4 minus 7/3, but I think if it's multiple choice, we're going to be able to do that mentally, and that's a safe place for us to stop. Find the volume of the solid generated by rotating n around the x-axis. Okay, that should be a little bit easier. Pi times the integral of, I'm just going to draw on this diagram. Okay, a is top minus bottom. This is 4 over x minus 0. Okay, pi times the integral of a squared minus b is x minus 3 squared. And it's b squared, so that's going to also need to get squared. And x is going to still go from 1 to 4, just like it was before. And then I'm going to square these things. 16x to the negative 2 minus x minus 3 to the 4th. And I can anti-differentiate this. When I plug in 4, I'm going to get negative 16 over 4 minus 1/5 of 1 to the 5th. Then when I plug in 1, I'd get negative 16 over 1 minus 1/5 of 2 to the 5th, or negative 2 to the 5th, so plus 1/5 of 32. And you could simplify that if you wanted to, but you know, I'm over here close to an hour and a half into this video, so I think I'm going to leave that unsimplified. Here we've got a calculator problem to finish us off, but you know, if you did this over multiple sittings, or even just in one sitting as you were preparing for the Unit 8 test in my class, I have to think you'd be pretty well prepared. We've seen a lot of stuff that I know you're going to be doing on that test. And you know, once you've seen all the different stuff with area and volume, you know, the discs, washers, the various types of cross sections, the perimeters, the arc lengths, and then those weird things like the magic line y equals k that cuts the region in half, or we've solved the related rate problems in class. Once you've seen everything, you've seen it, and there's not really all that much else that can happen. So A is bounded by y equals x squared and y equals 4. There we go. Find the area of A, gladly. Those are going to intersect at negative 2 and 2, so 4 minus x squared is top minus bottom. So that's 4x minus 1/3 x to the third. I would prefer to plug in x equals 0, and because this thing's got symmetry to it, I'm going to actually do that. So I'm just going to find the right half of it and then double it. So 4 times 2 is 8, minus 1/3 of 2 to the third would be 8/3. When I plug in 0, I'd have 0 minus 0. So let's see, 8 minus 1/3 of 8 is 2/3 of 8, times 2 is 4/3 of 8, 32/3. All right, find the volume of the solid generated by rotating A around the x-axis. Okay, so I'd have large radius is going to be 4 minus 0. Small radius would be x squared minus 0. So I'm going to be doing pi times the integral from negative 2 to 2 of 4 squared minus x squared squared. Okay, and again, you could use the same trick that I did up there, like leverage the symmetry and integrate from 0 to 2, but I think one of those is enough. I don't want to be confusing or anything. So 16x minus 1/5 x to the 5th from negative 2 to 2. Uh, 32 minus 32 over 5. This feels very familiar. Minus, when I plug in negative 2, I'm going to get negative 32 plus 32 over 5. And you can even see the symmetry in the antiderivative too. But you're going to get, what would that be, 4/5 of 32. You double it, that's 8/5 of 32. But I don't want to multiply 32 by 8. I feel like that's 256. Yeah, that would make sense because it's power of 2. But I think that'll be a safe place for us to stop. There exists a number k greater than 4, such that when A is rotated around the line y equals k, the resulting solid has the same volume as the solid in part B. Right? But do not solve an equation involving an integral expression that can be used to find the value of k. Okay, I don't remember this one. Now, if you were really concerned about the simplification here, you could just copy that bad number that I obtained in part B. But I do think I'm going to want to simplify this just for the sake of not having to write it all that much. 4/5, double that, that's 8/5 of 32, then multiply by pi. Yeah, 256 pi over 5. Okay, that's what this volume is going to equal. That's going to be the other side of my equation. Is this the answer? Now, I guess what we could have done is, to be safer, let's not rely on whether or not I computed that correctly. Let's set it equal to the integral over here, because that will be just as good. Okay, then over here, if we are going to rotate this thing around the line y equals k, then the large radius would be k minus f of x. We don't have f of x, but it's just x squared. So k minus x squared, that's my large radius, minus small radius would be k minus 4. Dx integrating from negative 2 to 2 and multiply by pi because we're finding volume with rotation. There you go. That's an equation that could be solved. We wouldn't want to solve it at all. That would be really unpleasant, but that's an equation. That's our answer. So finding the perimeter of A, that should be easy in comparison. We're going from x equals negative 2 to x equals positive 2. That's a width of 4. We're going to have this stuff, which, okay, if, you know, y equals x squared, dy dx, that's probably not visible to you. Oh, but I'm at the bottom of the page where it makes everything hard to be visible. That's 2x, so I'm going to add 4 plus the integral from x equals -2 to x equals +2 of the square root of 1 plus f prime of x squared dx. I'm not really sure how we're supposed to do that without a calculator. It might be that this is one of the forms that you could look up in the back of a textbook, you know, for how to anti-differentiate. But this is not something that would be expected to anti-differentiate in AP calculus without the use of a calculator. So I think this really meant to say set up but do not evaluate an expression involving at least one integral whose value gives the perimeter of region A. And I'm going to stop there because here I am 1 hour and 25 minutes in. This has been a really robust homework set. But like I was saying earlier, if you did all these problems, I got to think you're significantly more ready for a test on area and volume in calculus than you were before you did the problems. So that's going to be all for this video. Thanks for watching.